All right, so we're going to review analysis methods and types here. Talk a little bit about what you're going to be doing in the reading, and try to bring some of this stuff together. So we're thinking through. We talked about data, we talked about information analysis in the introduction, then we talked about collection. Now we've got the data. What do we do with it? So today we're going to talk about analysis methods and considerations, and do a little bit of an introduction on simulation itself. I'm not going to read all these charts. You can read them. What I want to use these for is go ahead and use them to shape your reading and kind of what you need to pull out of the reading. The key stuff will be in here. Analysis, we talk about collecting data, then you get into organization, so organizing all that data into something that becomes information, right? And then you take that and you do analysis with it as a verb there. That analysis will result in some analysis as a noun. So your analysis output, essentially, your results and recommendations. It's the process of studying the nature of something and determining its essential features and relations. And that's key when we get into operations analysis. We'll talk about the relationships within the system itself. You model a system, and then all of the relationships with the system really become what we're interested in within the analysis. There's lots of different types, but they all converge towards useful information and decisions that can be made by our customers. So different types here that we'll discuss. Structured analysis, which is really just deliberate conscious reasoning, using the techniques that you read about in your books. Operations analysis is really focused on systems and interactions of those systems. Forensics, now we're getting into some things that what forensic does is it pulls a lot of the past information. So it's more of a story. Understanding how those systems operated in the story that led to where we are today. Competitive threat assessment is the same as what you see before. You're modeling, but you're focused really on how do we shape the data that's related to the competitive nature or the threats around us. And then predictive does just the opposite of forensics. It takes what do we know about the system and tries to project it and forecast with it. So structured analysis is really what we're going to look in that book. A lot of what you're going to see and read in there, it's taking our approaches to problems and trying to be more structured about it so that we can avoid big efforts and big mistakes that we've had in the past. Think of the Bay of Pigs, think of WMDs, all those things that have led us down paths that have been big problems in the past. We've tried, what the IC community is trying to do with this book, really, and with its training, is get people to think through the problems in a mechanistic way, in a way that we can at least try to avoid some of the traps that we've fallen into in the past. There is enough reasoning that can be structured that we think you can be a lot more effective. There's still a lot of creativity and understanding relationships that drives people to come up with solutions, but let's make sure we're not falling into any of these traps that we just listed right there under the bottom. So intuition on the side, systematic thinking on the right. And this is basically pulled out of your book, but there are things we can do qualitatively. There are things that we can do quantitatively. So if we have data, we can do those things on the bottom. If we don't have data, let's at least follow some structured techniques, whether we have some known data, whether we have unknown data sets. We can still follow some structured techniques there that help us get to quality analysis moving forward that will avoid some of those problems that we've seen in the past. There's 8 families of structured techniques that your book talks about. Each one of these is kind of key. So think about all of these. If you're approaching a problem, which one of these is the most effective one to use? And you might use multiple, to be able to actually decompose a problem and do the analysis on it. But this is just a good way to categorize some of the approaches and effects. So choosing the right technique has a lot to do with just looking at the problem and finding which technique you think will actually just best avoid the errors that we talked about earlier. So, doing a definition, making sense of the data, generating hypotheses, all of these things you're trying to do so you can avoid those intuitive errors, or the errors that come with intuitive thinking on the right, which, presuming patterns, favoring the information that you're familiar with, ignoring the fact that some big gaps are there that you're just not even thinking about because they're not there. Those are the kinds of things that we're trying to avoid with these analysis techniques. We got a couple things here. Key techniques, scenarios and indicators is one of them. Frameworks for considering possible futures. Indicators that provide early warning. These are the kinds of things that you want to be looking at analytics techniques that will help derive those indicators from larger sets of data, which is going to drive us down the road here into our data analytics discussions, especially over the big data side. And then from hypothesis generation, this is one of those things that you're looking at and saying, well, there's a number of ways we can do this. We look at hypothesis and say, what are all the possible possibilities? We look at it and we say, well, how are we taking multiple hypotheses instead of just picking one? We actually compete them together to see which one comes up better. You do your argument mapping, just go through the hypotheses and see, well, what if we include deception as one of these hypotheses? What would that do? And how does the data relate to that? So again, we're looking at all these things and trying to figure out, as we look at this problem, are we not making mistakes? Are we assuming things incorrectly? And then do the analysis based on a technique that will avoid that. Operations analysis then takes this. This is the next kind of analysis. Here you're looking at we're going to represent systems and basically use simulation to represent those. There's force-on-force simulations. We do this in the Defense Department a lot. Social simulations, I think Department of State, and measuring overall sentiment of different areas. Physical effects, so right down to the physics, that they might be doing simulations with for systems that they deploy. All those are operations analysis. Any of those analyses are going to follow more of a systems engineering approach. So you have your concept operations, or you have your problem set in the top left, however you want to define the problem, that's the top left. You decompose it, you build requirements, you build your models and simulations, you implement those with the data, then you do your test and verification of those models and simulations, system level verification and validation, and then execution and analysis of those results. So as you're executing from a systems engineering approach, you're really decomposing and making sure as you go you're representing this thing correctly, and you're getting that verification validation loop as you go forward, verifying basically the system is correct and validating that it's operating in the correct way. A lot of times the customer is going to be involved in this execution, but they're going to rely on you as the analyst to actually execute all this stuff effectively. Other modeling techniques, communication hierarchies, network diagrams, interaction graphs. Again, all these things are, they may not be simulations, but they're communicating the relationships between components of the overall system. Problem statement is key. Anytime we're going to go into an analysis, you've got to spend all the time that you need up front to make sure you're asking the right question. I have an example here, and all I'm doing in this example is trying to describe. Here's a question that someone might want to know. How many patrol craft should the Royal Australian Air Force buy? That's a good question, but that's not something we can do really good analysis on. What you want to do is break that, decompose that into maybe a series of questions that you can actually do analysis on. How can they use it to most effectively protect shipping lanes? That's something we can put into a model, right? We can simulate that over time, simulate threats, all that kind of stuff. What's the infrastructure needed to support a detachment? That's something we can model as well with logistics supply chain models. What's the maximum ratio of protection to cost? That's something you'd want to do with some linear optimization. These are things that when you compose those together, now you've got probably some good information you can take back to decision makers and say, here's what we think as our analysis shows. Remember, 40% of the analysis is understanding the assumptions too. So, when we ask any of those sub-questions too, it's like, which shipping lanes do we really need to protect? Where are we going to, what's the cost of these things going to be? There's a lot of analysis assumptions that go into these things that we need to fill out those simulations with. Just make sure we get all of those up front done right. You do all that, then it's easy. You just execute the models, right? And you'll come up with answers. But you can really go off tangent and spend a lot of money and time in efforts that don't yield good results if you don't do those assumptions right, and if you're not asking the right question. So those assumptions really are the ground rules for the analysis. They shape the range of answers. And I've got this linear optimization of the prior question represented here. You'll have some assumption one, basically on the top that says here's the cost per plane. Then you've got an assumption on the far right there that says basically you've got how many you can actually base. There's some maximum number they can have. Then you've got a cost a price that they can have. They can only spend $1 billion on these things, and they're not going to buy none. So you kind of shape yourself at one of those points, based on linear optimization, one of those points is going to be the maximum answer. Now we have to go through and say which one gains them the most effectiveness over the questions that we had earlier. But those assumptions, wherever you base those assumptions, are going to drive you to one of those points. And that's, so it's key to understand those and make sure we're getting those right up front. Then once you've got that, sort of shape the analysis. What capability is needed? Can we afford the capability? What does the mission really look like? What does the logistics train need to look like for these platforms? All of that information should shape the model that you're creating to execute simulation across. So what's a model? A model is basically a representation of the real world system. And it can be done in Excel, like we're doing in this class, or it can be done in, you can build physical models. Any of those things, 3D models, CAD/CAM models, they're all representations that someone can use that isn't the actual system itself. So if we're looking at a scenario that's going to play out over time, clearly we need to do models of it because you're not going to be actually executing, force-on-force engagements just to see what happens. So, but they represent our knowledge of the system. They can be aircraft models, weapon effects, physics models, communications models, anything like that can be put together. Threat assessment, again, it's just take that modeling and feed it with what we've got from the IC analysis, in terms of SIGINT, MASINT, all that, and to understand kind of what are we looking at from the threat perspective and what do we know about their environment and what we have to deal with. Now we go to simulation. The difference between model and simulation, once you've got a model developed, you start executing it over time. That's what simulation is. So simulation is the execution of those models that you've created over time. It can be strictly digital, we call it constructive, meaning you put it into the computer and now it's just executing and spitting out an answer. It can be virtual, where we have people actually involved in it. And in those, so think flight simulations or multiple flight simulations where people are operating with each other. 3D games where you've got first-person shooter, Marines doing training, that kind of thing. There you've got simulation, digital and human, where the human really is just representing the most complex part of the model. The part that we really can't do very well in computers still, because it's just too complex to represent. And then Wargame on the other end of that, where it's almost all humans involved, but you're still creating a simulation of the events over time. So that's what happens with operations analysis simulations. You basically do movement over time. You represent those interactions of all those models and see what comes out at the end. Once you've bounded the problem with assumptions, questions, and the analysis from its sources, it's best to simulate those activities and basically test our assumptions and the knowledge of how they interact and our hypotheses to see what comes out. Different types of simulation. There's stochastic or deterministic. Basically, you model up the system, execute it, and spits out the answer. That's what we're doing this week. Actually, that's a question on your homework, so you just got the answer. Thanks for watching the video here. Stochastic is run multiple times. You replace some value of varying qualities and basically come up with new answers based on how you shape the model. You can have steady state or dynamic. So does it respond dynamically or not? Think of a flight simulator. That's going to be a dynamic response. It's going to change based on what the pilot is doing with that model. Continuous or discrete basically means are we representing the world over time, like we do in frame step simulations, or are we basically going from one event to the next? There are some different capabilities. One of them is much faster, and you can get a lot more answers out, but one of them sort of helps to understand the changing dynamic nature a little bit better. Frame step tends to be your sort of operator in the loop kinds of simulations. It can be local or distributed. You can have a lot of stuff hooked up over distributed networks. Executing is a large simulation. The trick there is making sure that everything operates with the same sort of level of fidelity so that you're getting some answers that actually make sense. There's assumptions too. The data sets that you used. Keep in mind in security, you're going to have a lot of different customers that only recognize their own data set. And it all has to be the same sort of level of fidelity, right? Don't make a really complicated weapon model and a not complicated aircraft model and put them together. It won't make any sense. Customers going to decide, basically, they're going to V&V it. They're going to say, yeah, this represents the problem that I'm looking at, and the answers to this will be useful to me. That's what VV&A is. Verification. Did I build the right thing? Did I build the thing right? And then the customer saying, yes, this should be used for this problem. So that is key. VV&A is key for these models, especially if they're going to be used for sourcing or for making big decisions. Credibility is important. You can do VV testing all day long, but it's got to get to the point where they say, yeah, this is good enough, and we're going to execute on this.